My name is Oliver. I'm the bad guy Rob mentioned. I'm going to talk about solving engineering problems with our PDE tools, and yeah, I'm going to give you a little bit of an overview. I'm giving another talk this afternoon, a little later. It's about how to write your own PDE solvers. That's a bit more in detail. You're going to see a little bit more code, I guess. It's probably more for people that really want to delve into the stuff. This is a bit more of an overview talk, so just that you know a bit of what we're going to do. So solving engineering problems, that's a huge topic. Obviously, Wolfram Research has a few products that are in that area. There's System Modeler, and there's been a few. And in the Wolfram language, one of the tools to use for solving engineering type problems is, of course, NDSolve, the numerical differential equation solving tool. NDSolve, and that's the thing I'm going to talk about, NDSolve. And NDSolve itself is probably one of the most complicated functions within Mathematica. It does a lot of things, so you can solve ordinary differential equation, boundary value problems, delay differential equations, hybrid and discontinuous equations, differential algebraic equations, and partial differential equations. And in the partial differential equations division, you can use a specific method for solving PDEs over rectangular regions, or, and now that's the new part, over arbitrary shaped regions. So we drill down a little bit of where my comfort zone is. I'm going to talk about NDSolve over arbitrary shaped regions. So how does that look like? You use the function NDSolve value. You specify a PDE operator, like the negative Laplacian equal to 1. You set a couple of boundary conditions. U is the dependent variable that we'd like to find the solution for. And you say that on some parts of the boundary, the value U is supposed to be 0, and on other parts of the boundary, the value is supposed to be 1. And the region is defined by x comma 0, 1, and y 0, 1, where y are the independent variables. NDSolve will return you an interpolating function, and that's an object that you can immediately use to plot, to visualize. So that's the solution of that specific problem. So that's how NDSolve has worked in previous versions, and that's exactly the same input you can use nowadays. Now, in order to solve PDEs, you basically need three things. You need a region over which you would like to solve the PDE. You need the PDE as such, of course, and you need boundary conditions. And the boundary conditions are kind of the interface between the region and the PDE. So that's an intermediate layer, so to speak. In NDSolve, if we do a problem setup like that, you specify a region. I just use an arbitrary region here, like a disk. You specify an operator, the Laplacian, and then we can have something like a boundary condition, a Dirichlet boundary condition in this case. And there, in this case, you see I specified that the dependent variable u is supposed to be 0. And the second argument specifies where that boundary condition is supposed to be active. So everywhere where x is larger than 0, this boundary condition is going to be active. And then you call NDSolve value again with the operator, the boundary condition as we specified them, and that will return you an interpolating function. And again, you visualize the solution with, for example, plot 3D. And also note here that, again, we specified x and y are part of this region omega. So that's in principle how it works. So the question is, which type of PDEs can we actually solve? So don't be disappointed. We can only solve one PDE. But we'll get to that. So this one PDE is this big thing up here. And you see a second-order time derivative, a first-order time derivative, a diffusion kind of coefficient. Here's a convection operator, another convection operator, a boundary, a load in this PDE. And if you look at the PDEs I've listed here, those are some of the classical ones. And if you see the blue parts, those are the components, so to speak, that are active in these respective PDEs. So it's kind of a Lego system where you can combine different components of PDE operators and build your own PDE together. Now, we're going to look at a few specific examples. So here I have a Poisson type of equation. I want to specify Dirichlet boundary conditions. So let me, this is the region I'm interested in. And the red and the blue mark specify where I want to place boundary conditions. So first, I set up this implicit region, which specifies the region that I want to solve my PDE over. I specify the operator again. And I have two Dirichlet boundary conditions. One says the dependent is supposed to be 0, and that's the one that's on the left-hand upper side. And then I have a second Dirichlet condition that says the value is supposed to be 100, and that's in the inner circle part of that specific region. Again, I call NDSolve value with all the parameters we specified, and I can plot the solution again with plot 3D. Same thing again. On the boundary, we can specify 3 different types of boundary conditions. We can specify Dirichlet boundary conditions. That's what we saw so far. I'm going to talk about the Neumann, or we're going to see examples about the Neumann value just now. Dirichlet condition means take the dependent variable and give the dependent variable a specific value at that point. A Neumann boundary value specifies how much flux goes over the boundary, how much of the material or whatever you're modeling is going over a boundary. The Neumann value that we can specify is something called a generalized Neumann value. And yeah, I can show examples about that a little later. If you do not specify anything on the boundary, that defaults to a Neumann zero boundary condition, which means basically, yeah, you have an insulating wall, for example. That's what Neumann zero means. So not specifying anything means Neumann zero boundary condition. OK, the same region as I had previously, and we have 2 different boundary conditions. Now we have a Dirichlet condition again on the upper left-hand part, and I just specified a Neumann value, or a generalized Neumann value in this case here, where I have -2 times the dependent variable on this inner boundary, on this inner circle. And again, NDSolve solves the equation and visualizing with plot 3D. So I've left that away now. Here's a 3D example. I'd like to model a heat sink. So that's the boundary mesh I have here. I've used a finite element specific tool to add specific markers here. So I have this red region and the green region. And those are useful when I want to specify boundary conditions. As I can say, I want a specific boundary condition in this red region and in the green region. It makes it a bit easier sometimes to specify them in this way. We'll see that just now. And the And the equation I want to solve is a Laplace type of equation. OK, I have 2 Neumann values. One is using this, is active on this element marker 1. That's one of the regions. And the second one is active on the element marker 2. And this first one is, it's not too important to understand the exact physics of this. One is just a flux over the boundary where we specify a specific Neumann value. And here we specify something in relation to the dependent variable of u. The specification now is I have the PDE operator and set that equal to the boundary conditions. And the reason why that's done this way will become apparent just now. Then I call NDSolve on that and visualize the solution. So here is now the solution of this specific PDE problem. That specific mesh had a little more than 100,000 nodes. So that means the system matrices are 100,000 by 100,000. And we solved that in something like 4 seconds with NDSolve. So it scales fairly well. These PDE Lego components have something that are coefficients. And these coefficients, so they're marked in red in the slide. And these coefficients may depend on space and time. They cannot yet depend on the dependent variable, so we cannot yet solve nonlinear problems with the finite element method. So what I have here is I have a rectangular region out of which I cut a piece out. And on this inner boundary, I'm going to set a specific potential. And the outer boundary is not going to have, is having a 0 potential. And the PDE I would like to solve is something like this. So this epsilon r is a function of x and y. And this epsilon r is defined if y, so the y component of this region, is smaller than a specific number I've specified, a specific number, a specific height that goes through that region. Use these material parameters, and if not, use those here. This is how I specify the entire PDE. I specify Dirichlet conditions. On the outside, the dependent is 0, and on this inner part that I cut out, I have 10 to the power of 3. When I solve that, so I put that into NDSolve, you see the discontinuity here in the two materials. And you see that there's a kink here in the solution. So NDSolve can actually handle discontinuities in the coefficients. One thing I'd like to point out is the fact, and that was what the question was in essence about, is NDSolve actually sees this coefficient and sees that there is a discontinuity and automatically introduces this material boundary. So you don't even have to specify. NDSolve can analyze the PDE and see, OK, this is a different region, and it's better for myself to divide that region such I can come to a better solution. Yes, it's exactly the same. It's just the way the result is returned is a little different. Yeah. OK. Here's quickly a transient problem. So what you see here is a pipe. Inside that pipe, you have a hot liquid. Outside is, I don't know, room temperature, whatever. And these holes that you see in the pipe are cooling ducts. And I'm going to look at this specific symmetrical section here. What I want to know is, like, what is the heat distribution in this pipe when I switch on the cooling liquid, when the cooling liquid comes inside in this region. So I have a Neumann value that is time dependent now. So it says if t smaller than 10, then I use minus 100 times t. I ramp it up in 10 seconds. And the maximum is minus 1,000. That's the amount of heat that cooling liquid can absorb. This is the second part is the specification of, where's my point? There. The second part is the specification of where that region is active. I have two Dirichlet conditions. One is on the inside, that's the 200 degrees, and that one is on the outside, so it's 15 degrees. This is the PDE operator again. I use NDSolve value as with a time-dependent problem. And, right, so excuse me. So the first thing I do is I compute myself an initial condition at time t0, because NDSolve needs an initial condition. And then I use that initial condition to start NDSolve value. So, and this here is the solution. So now you see at different times in the solution how the heat is absorbed when I switch on this, this cooling liquid. OK. NDSolve, so what internally what NDSolve does, it analyzes the coefficients or the input function you gives. It extracts the necessary components and auto-compiles those and then runs. Yeah, it does that. That's right. Here's the contour plot of the solution at time 25. OK, so we've warmed up now, and now we'll discuss systems of PDEs. So I said that we're only interested in one PDE. That's still true, but we can couple as many of them together as we like. In this example, I'm going to show two PDEs coupled together, but there can be arbitrary many. What you see now, I have the dependent variable u and the second dependent variable v. So this diffusion coefficient, we have a second diffusion coefficient. And in the second equation, we also have the dependent variable u and the dependent variable v. So you can now cross-couple between these two coefficients. That's a very general way to express PDEs. Dirichlet conditions are now u plus v equals r, and Neumann values also now have a u and a v component. So it's getting a little more involved. So here's an example from structural mechanics. I have a rectangle from 0, 0 to 5, 1. I have Young's modulus 10 to the 3 and a Poisson ratio of 33 by 100. I have a plane stress operator. I say, and that operator works in the dependent u and the dependent v. One is the x direction and one is the y direction. I have no deformation in the x direction, and in the y direction, I put on the right-hand side, at x equals 5, so on the right-hand boundary, I put a force of -1 unit in the downward direction. And on the left-hand side, u and v are held fixed at a fixed position. I call NDSolve value. This is a coupled PDE. It now returns 2 interpolating functions. And this is the visualization of the deformed object now. So you see on this right-hand side, I've put a force of -1 in the negative y direction, and this is the deformation now. I've written a small function that's not part of Mathematica right now to compute the von Mises stress, so you can also do something like that. Here's an example from fluid flow. So this is a Stokes equation. On this left-hand side, we have an inflow boundary condition in the x direction. On the right-hand side, we have a pressure boundary condition. We specify a specific pressure here. These are the equations, the 3 coupled equations we're going to solve. They're in u, v, and p. U and v are the velocity in the x and the y direction, and p is the pressure. I specified, to model this problem, I specify an implicit region. I have this Stokes flow operator with a coefficient, u, v, and p. And there's no force on that operator. I have a Dirichlet condition that models the inflow condition. So u at the left-hand side is specified by this formula. U and v on all other sides are set to 0. And the pressure at the output is also set to 0. We call NDSolve. We give an interpolation order. And this allows us actually to use a higher order interpolation for the velocity than we use for the pressure. That's something very neat because that stabilizes this specific method. For this specific problem, it stabilizes the computation. And here's a visualization of the flow field in this duct. 3D, here's an example from structural mechanics. I have a crankshaft, and that's a graphics object. I use the function discretize graphics and feed that into this finite element mesh generation tool. That's 175,000 tetrahedras now. I have this stress operator in 3 components, u, v, and w. So it's in the x, y, and z direction. And again, I have a force in the negative z direction, and Dirichlet boundary conditions on the left and the right-hand side. NDSolve takes about 6.5 or 7 seconds on this computer. Not on this computer, but on a regular laptop. And here's a visualization. In red, you see the deformation of the crankshaft when it has been pushed down, but held in place on the left and right-hand side. OK. This is all that had been there in 10.0 and 10.1. This is new in 10.2. We can solve eigenvalue problems. So the single PDE we've seen before can be solved as a lambda equals lambda u, an eigenvalue problem. And here are a few examples. So I can now, the new function that we're using now is ND eigensystem. The negative Laplacian. U is the dependent variable from x from 0 to pi, and give me 4 eigenvalues. These are the 4 eigenvalues, and I can plot the 4 corresponding eigenfunctions. Here's a little bit more of a more complicated example. So now we've changed the region to a disk, and also specified a boundary condition. So this is a constrained eigenvalue problem. We say the dependent variable is 0. True means everywhere on the boundary. These are the corresponding values. And this is the interpolating functions, a plot of that's one of the interpolating functions. And here are some of the plots of those. OK, oops. So this is a picture from Wikipedia. and someone took a mini car and cut it in half. That's what you see here. So it's cut, and you can look inside. What I used is the image processing masking tool and cut out or made a polygon of what's the boundary that's inside this mini car. I used boundary discretize graphics to discretize that boundary, and I fed that into Eigensystem to find the acoustic modes in that mini car, and I wanted to compute 6 of those. And this now is a superposition of the first eigenfunction in that mini car. That gives you the pressure of the acoustic pressure in that car on the first eigenfunction. Okay, we're going to switch topic a little bit again. This has been added in 10.3, and that is using PDEs and events. What this means is you can have an event during a time integration with PDEs. Imagine you have a room that has 3 solid walls and a glass front, and over that glass front the heat is dissipating or coming into the room depending on the outside temperature. I have an outside temperature modeled by a sine function, and 15 degrees plus 10 times the sine. This is the model of the room, some material constants. I have a Neumann value. That is the outside temperature minus the dependent variable. And now, now the event is supposed to trigger if the temperature in the room goes below 18 degrees, or if the temperature is above 20 degrees, then either the heater is supposed to be switched on or switched off. And that's done with a discrete variable. That's the variable A in this example here. So if A equals 0, we'll set the event time to t and change A. And in this case here, if the event is if the evaluation of the function u at the position is higher than the trigger time t high, or trigger high, then we switch the event off, or the machine, the heater is switched off. This is the PDE model, so a Laplacian, and this is the actual heater inside of the region. That's the heater that's switched on. This heater is also ramped up and ramped down. So if you switch on a heater in a room, it just doesn't produce the heat. Or if you switch it off, it's still hot and needs some time to cool down. All this information is then, again, plugged into NDSolve value. It computes an interpolating function. And here is the result for this specific example. So what you see here in this orange tone is the outside temperature. This is the 20 degrees mark. This is the 18 degrees mark. So initially, the heater is off, so it switches on. It overshoots a bit, starts to switch off and cool down. But since the outside temperature is still rising, the temperature in the room is also rising. Only when it starts to fall down, this also begins to fall down. And when it reaches a temperature that's below 18 degrees, the heater is switched on again. It shoots, since the outside temperature, it's night now. We switch it on, and it overshoots again a bit. It switches off. And so you see that that's kind of the event switching it on and off. OK, so that's basically what I want to say. As a summary, I'd say NDSolve rocks. We can solve linear, variable coefficient, transient systems of PDEs over arbitrary regions in 1, 2, and 3 dimensions. My email is ruebenkoenig@wolfram.com. It's not a secret. If you work on PDEs or something like that and want to discuss that with me, please send email. Thank you for your attention.